there's more to theorem 215. So this is part 6. This is our last part for this toolkit theorem. This one is about pointwise supremum or infimum, which is what I like to call it, of a sequence of measurable functions. So let's say you have a measurable space X, sigma algebra A, and let's suppose you have a sequence of measurable functions. So I didn't write it this time, but measurable means with respect to A and with respect to the Borel sigma algebra on R. And we're assuming about this sequence of functions that if you focus on any particular point X and look at the sequence of real numbers there, then that's bounded, always bounded. So this assumption allows me to define a sort of pointwise supremum and infimum. So let's call these capital S and capital I, for standing for supremum and infimum, where capital S at any given point X is the supremum running over all n, and capital I is the infimum running over all n. Then the claim is that if the fn's were measurable, then these functions that you get this way are measurable. So one fun thing you can think about is if we replace the word measurable by continuous everywhere here, would this still be true? If you take a pointwise supremum or infimum of continuous functions, would that be a continuous function? Okay, so let's look at the proof of this. So we will actually just do one of them. So we'll handle the supremum only. The infimum is similar, kind of. And I'll comment about that at the end. So let's assume the hypotheses. Sometimes I forget to write that, but I do like to write that. I mean, how do you know I'm not trying to do a proof by contradiction or something? Yeah, so we're assuming we've got our measurable space, sequence of measurable functions, and the function S is defined. Now the first thing I'll do is reduce it from being a problem about supremum to being a problem about maximum. So let's define a sequence of functions gn on x by, so remember our original sequence of functions is fn. Define the gn's by gn of x equals the maximum of all the fn of x's running up to n. Okay, so take the maximum of these finitely many real numbers to get g sub n of x. Now, I claim that the supremum, the pointwise supremum, is the pointwise limit of these gn's. So this is what I claim. And if I can prove this, then if I prove the gn's are measurable, then by the previous part in the previous video, we will have that the that S is measurable. Right, so let's prove the gn's are measurable, then S, being the pointwise limit of measurables, would be measurable. And let's also prove this claim, that S is the pointwise limit of these. So claim first. Now this is a statement about pointwise convergence, so let's let x be an arbitrary point and then prove convergence at that point. Okay, let epsilon be greater than 0. This is what we're good at in 118, right? Now we're trying to show that there's an n large enough so that g sub n of x is close to s of x. Now remember that S of x is the, it's off screen now, but S of x is the supremum of the f sub n of x's, right? So if I draw a picture of the real line, if this is S of x, and if this is S of x minus epsilon, which is strictly to the left, then since this is the supremum of the fn of x's, there should definitely exist some n such that f sub n of x is passed here, right? Is somewhere in between here. So what I'm using here is actually this lemma that we've used a million times. This is from our textbook by Abbott. This lemma about Supremum. Okay, you've used this many times. So from here, there is some, let me call it capital N. There's some capital N such that the collection, such that f sub capital N of x exceeds this thing, which is strictly to the left of s of x. Like that. So that's using that basic fact about Supremum. So let's see that this big N works for proving our convergence statement that we want. So let little n be anything bigger than or equal to big N. Then if we look at Gn of x, well, on the one hand, it's definitely bigger than or equal to f big N x, because it's the maximum of a bunch of things, and this is one of the things in the list, right? So this is a maximum of a bunch of things in a list, of which this is one of them. So this is bigger than or equal to that. And this is bigger than s of x minus epsilon. And again, this is the maximum of a bunch of things in a list, and they're all f sub something of x, right? So that means it's one of them, right? This is one of the items in this list. All of the items in this list are less than or equal to the supremum of a collection that contains those items. So let me center this better. So this proves that the G sub n of x's converge to s of x, which is what we need for pointwise convergence. Just do this for arbitrary points. So that proves the claim. Let me box that in. Then if the GNs are measurable functions, then we're finished, right? Because of part 5. So let's write that. By part 5, if the GNs are measurable, then so is the pointwise supremum function, capital S. So are the GNs measurable? So they're defined to be this kind of maximum of a bunch of measurable functions, right? So is the pointwise maximum of a finite collection of measurable functions measurable? Well, you can always sort of view the maximum as an iterated binary maximum, right? So like Gn of x is, you can view it as the maximum of f1 of x with the maximum of the list starting from f2 of x running up to fn of x, right? So you can always view it as a binary maximum, and then if this is measurable and this is measurable, a function of x, then your problem becomes, can I verify that the maximum of two measurable functions is going to be a measurable function, and so on and so on. So this could be broken down into a binary maximum. So by induction, it's sufficient to just show that the maximum of two measurable functions is measurable. So let's say it's sufficient to show that G sub 2, which is the maximum of f1 and f2, is measurable. So if I take two measurable functions and I take their maximum at every point, do I get a measurable function? This is actually, you could view this as a special case of the presentation problem that I gave you guys last time, where you pretty much show that if you have any kind of continuous binary operation, I don't know why that's in quote, just continuous binary operation, and you apply it sort of pointwise to a pair of measurable functions, then you get a measurable function. So is taking the maximum a continuous binary operation? Well, here's a plot of the maximum of two variables. Looks pretty continuous. Okay, but that's actually way overcomplicating things. I don't really want to rely on that presentation problem, although it's cool that it applies to this situation in the same way that it would apply to showing, say, that the sum of two, or even the product of two measurable functions is measurable. All right, so in this case, we don't need to overcomplicate things so much because it's actually a really easy case. So I'm just going to do it directly. So here's what I mean by directly. Again, let C be a real number. Then our goal is to show that if I so let me just write the goal. Goal is to show that if I take the preimage of this thing, which this is one of the if over all C and R, these things are generators for the Borel sigma algebra on R, right? So my goal is to show that this is in fancy A, the given sigma algebra on capital X. So this is the set of things that G2 maps to something less than C. So let's break it down. So this is a set of x's such that G2 of x is less than C. Okay, but G2 of x is the maximum of F1 and F2, right? So let's just write that down. Max F1x, F2x less than C. Okay, but to say that the maximum of F1x and F2x is less than C is to say that both F1x is less than C and F2x is less than C. Right? That's what it takes for the maximum to be less than C. And this is now the preimage under F1 of this thing being intersected with the preimage under F2 of this thing. And these are both in fancy A, right? They're both in the sigma algebra, because F1 and F2 are assumed to be measurable. And so the intersection, sigma algebra is closed under even countable intersection, so this binary intersection is definitely in the sigma algebra. So we're done. Well, we're done handling S. We're done handling capital S. We've now shown that capital S is a measurable function. But what about I? Is it really similar? So I guess instead of max, you'd have min here. And you could probably do this proof just fine. Instead of focusing on stuff to the left of S, you would be focusing on stuff to the right of I. Fine. That's not so bad. I think there's a little bit of a difference here when you take the preimage of one of these things, because you would have, you'd be focusing on showing that the minimum of two measurable functions is measurable. So then here you'd have a min showing up. And to say that the min is less than C does not break down in this same exact way as it does for max. Well, I guess you'd get a union here rather than an intersection if you had a min here, which is the union of things in fancy A are still in fancy A. So I guess that's fine. All right, so I'm going to erase this kind of. I think it's actually more similar than I thought. Another thing you could have done, I guess, to handle that case is to flip around these sets and use a different generating set for the Borel sigma algebra on R. Yeah, so that would be fine. Another way is to write the infimum of the fn's as the negative of the supremum of the negative fn's, and then use the earlier results that linear combinations, like for example taking the negative of something, of measurable things is measurable.